Hello, good evening, and today our team will be talking about infrared spectroscopy.
Electromagnetic radiation is a form of energy that is produced by an oscillating electric and magnetic disturbance. Electromagnetic radiation can cover an enormous range of wavelengths and frequencies. This range is known as the electromagnetic spectrum, which is divided into several regions, but in this presentation we are only going to talk about the infrared range. Infrared is in the range of the electromagnetic spectrum between the microwaves and the visible light. It has frequencies from about 30 terahertz to about 400 terahertz and wavelengths from about 100 micrometers and 740 nanometers. This light is invisible to the human eyes, but we can feel it as heat if the intensity is sufficient. A significant discovery about all these electromagnetic waves are the velocity of all of them travels at the speed of light, and it is well known that the wavelength times the frequency equals to this speed. Also, by the work of Einstein, Planck and Bohr indicated that in many waves the electromagnetic radiation could be regarded as a stream of particles or quanta for which the energy E is given by the Bohr equation, which is the Planck constant times the classical frequency, and this equals this energy. This means that the processes of change, including those of vibration and rotation associated with the infrared spectroscopy, can be represented in terms of quantized energy levels. But what is infrared spectroscopy? Infrared spectroscopy is one of the most important analytical techniques available today, which is based on the vibrations of the atoms of a molecule. It takes advantage of the fact that molecules absorb frequencies which are characteristic of their structure. An infrared spectrum is commonly obtained by passing infrared radiation through a sample and determining what fraction of the incident radiation is absorbed at a particular energy. The energy at which any peak in an absorption spectrum appears corresponds to the frequency of a vibration of a part of a sample molecule. One of the great advantages of this technique is that any sample in any state can be analyzed. It doesn't matter if it's a gas, a solid, a powder, a gas, and any surface can be analyzed.
Okay, the molecules are constituted by atoms linked by electrostatic forces, which move continuously in position of equilibrium, allowing the molecule to present translational, rotational, and vibrational movements. The total number of movements is known as degrees of freedom. For example, if a molecule has n atoms, it will have 3n degrees of freedom, and 3 of translation, 3 of rotation, 2 if it is linear, and 3n minus 6 of vibration, and 3n minus 5 if it is linear. Vibration movement can be decomposed into oscillation in which the atoms move in phase and are called normal moves of vibration. Only an interaction between the infrared radiation and the vibrational states is possible if the electric vector of the incident radiation oscillates with the same frequency as the molecular dipole moment, and it produces an absorption of energy in form of resonance. A vibration is active infrared only if the molecular dipole moment can be modulated by a normal vibration. This means that not all molecules give infrared spectrum. For example, nitrogen and oxygen are not active in infrared because the vibration of their links do not change their dipole moment. There are two selection rules for infrared spectroscopy. A specific selection rule: only transition between consecutive vibrational states are allowed. The transition from the energetic level 0 to 1 is the fundamental one. Global selection rule is when molecular vibration has to produce an oscillation dipole to absorb energy. In complex molecules, it is useful to analyze the symmetry of their vibration to determine which are active. Symmetric stretching is not active in infrared because the dipolar moment is not altered, but antisymmetric stretching, scissoring, and rocking are active.
Now, in this group we will talk about two different methods of infrared spectroscopy to identify the molecules with which we are working. The first one is the Fourier transform method, and it uses an interferometer that the same use as Michaelson model. This one consists of a light source and two mirrors. The first one is in a fixed position, and the second one is mobile. It can be moved. A beam splitter, the sample will be placed here, and the detector. Now, this works by shooting a beam by here, and then the beam splitter makes the beams to go into two directions. At first, this distance of these two mirrors will be the same to the beam splitter, and thus we will have constructive interference here. But the thing is that we can move this mirror in a way that we get either constructive or destructive interference and all in between. The beam that reaches here is a function of two things. The first one is the sample, and the second one is the distance by which we are moving the mirror. And thus we can create a function of both, of the intensity or the wavelength of the beam that reaches here. But before doing that, we need to make at least two samples. In this one, we have to make at least two interferograms. This one, these reach the detector. And then by making Fourier transform of the sample and then of the sample and the air, and we make a ratio between them. Why do we make a ratio? To only get the sample, the thing that in which we were working with. We don't care about the environment. And this is the spectrum that we are looking for. This is the spectrum that will tell us what are the components of the molecule. Now, to find the components of the molecule, we need to know the transmittance of the thing, the height of this graph. The units of this is transmittance that goes from 0 to 1, and this one is wave number. For example, we have this graph of certain functional groups of molecules. We know that CH bonds come from 3000 wave number, and here we can have the range at which we may find them. Now, what happens if our sample cannot be described using this method? Why not? Because certain samples have their surface are reflected in such a way that when a beam reaches, it goes through all directions. Like in this case, we will expect this, but since the surface is rough, for example, a rock, we'll go through all directions, and we cannot make this one because it only uses focused beams. And thus we use another method that is diffuse reflectance. An example of this material is carbon. Now, how does diffuse reflectance work? Well, basically, we need to make a powder of the sample that is 90% potassium bromide, KBr, and 10% the sample. Why 90% and why 10% of this? Because we want to make a spectrum of it. A common mistake is by putting a lot of this and little of this, but that's not going to work. We will get a spectrum that is too hard to analyze. So 90% and 10% and 10 of this is perfect. Now, we put our sample in the middle of two mirrors that will make all the light passing through to a single point. We shoot we shoot two initial beams at them, and we'll pass through them, and thus catching all the diffuse irradiance caused by the sample. And finally, which will reach a detector. This detector will be able to make the same spectrum as the others, but this takes maybe a little too much time for that we have.
The infrared spectrum is useful for space exploration because, unlike other electromagnetic waves, infrared is not absorbed by the dust or other substances in space. The water particle in the Earth's atmosphere interfere with the spectra, so it's preferable to conduct these experiments in the stratosphere or in deep space. The spectrometer in these missions are not that different. The only difference in the design is that we only care of the radiation emitted from planets or stars. The variants in the other spectrometers are that we don't need to care of the sample or the source of the radiation. Because of the beam, we intercept is unrefined, it needs an optical path. In the Harmer's spectrometer in Sofia, the stratospheric observatory of infrared astronomy, we use chambers with lenses, collimators, and filters. A collimator is a device that narrows a light beam to be aligned in a direction. The setup of internal curved lenses helps us to change the orientation of the particles. The Doppler effect is very important in this design because the wavelength that we acquire will help us to verify the velocity of planets and celestial bodies. The objective of these experiments is to locate particles of oxygen, hydrogen, and water to prove existence of life in other planets or locate suitable planets like the Earth. A very successful example of this spectrometry in space exploration is the satellite ISO, the Infrared Satellite Observatory. It was able to find water vapor in the atmosphere in Titan, one of the moons of Saturn.